Hello colleagues, my name is Phoenix and this is the 9th episode of my SKSE modding tutorial series. In this video I'll talk about enums. This simple episode will prepare you for the next videos, bitfield and enum plus bitfield. Here is the plan for today. We'll break down why enum is needed, how to use it, look at the examples from CommonLib, and most importantly, learn how to work with it in IDE. Timestamps are in the description. Let's start with the motivation. A player has several states: alive, dying, dead, unconscious. And the player's weapon also has several states: sheathed, drawing, drawn, sheathing. To handle these states, a beginner would create two int variables, life state and weapon state, and keep the mapping of number to their meanings in their head. These constants would be used in the code. They are also called magic numbers. Their meaning isn't clear at the first glance. This approach has a problem. You see a check like if weapon state equals 1 in the code, and you don't understand what 1 stands for. Sheathed? Or maybe drawn? It's easy to mix up two constants, and when you have dozens of such numbers, keeping them all in your head is impossible. A more experienced programmer would create named constants for each state value and use them in the code. The magic numbers are gone, the code reads like plain text, and the chance of mixing up constants within the same group is reduced. However, this approach is still not type-safe. You can compare variables from different groups, for example, life state with drawing. This can happen especially when constants from different groups are named similarly, like none or total, or when a constant from one group has a name that also fits the other group. Since variables are of type int, the compiler won't forbid such comparisons. But the variables life state and drawing are semantically different, so comparing them makes no sense. You'd want such code to not even compile. Of course, in C++ you can overcome this problem with your own solution. But the language already provides a built-in mechanism, enums. An enum lets you give names to numbers once, and then use those names everywhere. It is no longer an int, and enumerators from different groups cannot be compared with each other. Here is an example. Now the code speaks for itself. Instead of numbers, we see explicit drawing and shading. Now let's talk about how to use enums in C++, how to declare them and how to refer to their values. The declaration looks like this: the enum keyword, then optionally class keyword, then optionally the name of the enum. Then, inside curly braces, you list the enumerators in the order you need, optionally assigning values with equal expression. Why write class keyword and what the differences are, I'll cover that later. We are starting simple. Let's figure out how values are assigned in an enum when we don't specify them explicitly. Most of the time, the specific numbers don't matter to you. The main thing is that different names correspond to different values. Occasionally you might even need repeating values, but more on that later. So, automatic numbering is defined by two simple rules. Rule 1. If the first enumerator has no explicit value, it will be 0. Rule 2. Each enumerator, without an explicit value, will be 1 greater than the previous one. These rules lets you have an enum as a list of enumerators, with no value specified at all. If you need a specific value, you assign it explicitly. The weapon state example is equivalent to the following. Here is another way to define the same enum. As you can see, the order of elements can be arbitrary, and some values can be left unspecified. I am showing this example only to illustrate how the rules work. Don't write code like this. it's harder to read and maintain. In real code, explicit values are often used for logical groups of enumerators. You set the starting value for the first enumerator in each group, and all following ones automatically get +1. All examples up to this point have declared scoped enums. If you omit class keyword in the declaration, you get an unscoped enum. For an unscoped enum, specifying a name is optional. Unscoped enums are legacy from the C language. Scoped enums were introduced in C++ 11. It's generally recommended to use modern enums, but legacy ones are sometimes convenient. Both kinds appear in CommonLib, so I'll explain the differences in how they're used. There are two differences: scope and type conversion. The first difference is reflected in the name. Enumerators of a scoped enum can only be accessed using the enum's name, whereas enumerators of an unscoped enum are visible outside it. An unscoped enum can be unnamed, while a scoped one cannot, because its name is required to access it. The second difference: scoped enums do not implicitly convert to an integer type. This means you cannot pass enumerator weapon state chess or a variable of type weapon state to a function that expects an int. This is type safety. The compiler won't let you accidentally pass a weapon state to some unrelated function. To tell the compiler that you know what you are doing when converting to an integer type, you need to use static cast. The very need to write static cast will make you think twice about whether the conversion is correct. Variables of a scoped type can be compared with each other without additional casts. Arithmetic operations on an unscoped enum are allowed, but the result will be an integer type. An unscoped enum implicitly converts to bool, so if weapon state will compile, while for a scoped enum you need an explicit cast. It's important to understand, an enum is more than just a group of named constants. It is a new type associated with an integer type. A variable of type weapon state can hold any value that fits in the underlying integer type of the enum. The declared, shared, drawing, and the rest are just named constants of this type that can be accessed by their names. Nothing prevents a variable of type weapon state from getting a value that is not among the declared enumerators, for example via static cast. The compiler does not check that the variable holds one of the listed names. It only guarantees type safety between different enums and ints, but not that the value belongs to the declared set. There are libraries that implement these checks though. By the way, regarding which integer type actually underlies an enum. Up to this point, I've been saying just integer, because it's not always int. This type is called the underlying type. It can differ from one enum to another. The programmer can specify it explicitly, or the compiler can determine it. And the rules for how it's determined differ between scoped and unscoped enums. According to the standard, the underlying type must be large enough to hold all enumerators. To set the underlying type, use colon and then the type name. Same syntax for both scoped and unscoped enums. MSVC does not follow to the standard here. Now I'll explain how the compiler chooses it. With scoped enums, it's simple, the default type is int. In an unscoped enum, the underlying type is implementation defined. If the declared enumerators don't fit into an int, the type will be larger, for example long or unsigned long. The compiler should not allow you to create an enumerator with a value outside the range of the underlying type. Also, in unscoped enums without the type specified, you cannot declare an enumerator with a value that does not fit into any of the valid types. For example, currently in GCC even unsigned int 128 is used. MSVC does not follow to the standard here. This program compiles, the asset accepted, function foo returns true, function bar returns false. Obviously that's not the result you'd expect, right? Since the asset accepted, the underlying type remains int, and the large number gets truncated to 1 upon conversion. With the GCC compiler, things are different. The underlying type is chosen as unsigned long, and the functions behave as they should. To make MSVC choose type correctly, you need to use the enum types compiler switch. With it, the type long is chosen, which confirms that the type is implementation defined. This is a good reason to specify the type manually. The second reason is relevant to CommonLib developers and SKSE plugin authors. In previous videos, I've talked about how important it is to correctly figure out the argument and return value types when hooking or calling a native function. If the underlying type of an argument in the original function is one thing, and in your code it's another, you'll get the same bugs as when you guess the argument type incorrectly. If you've reverse engineered a structure where one of the fields is an enum, it's critically important to get right not so much the sideness of the underlying type, but its size, because this affects alignment and all subsequent field offsets. Our goal is for the field's offsets in our structure to match the offsets in the original game. Then, in our hooks, we'll be reading and writing exactly the data we expect. That said, for documentation purposes, most enums in CommonLib do have an explicit underlying type. Before we look at examples from CommonLib, I'll recap the key points. An enum creates a new type associated with an integer type. Inside the enum body, you can create named constants, enumerators. The auto-numbering rules are designed so that the programmer often doesn't need to specify values manually. There are two kinds of enums, the unscoped one left over from C and the scoped enum introduced in C++11. The two main differences are scope and the presence of implicit conversions. The integer type of an enum is called the underlying type, and it's better to specify it manually. As in any large project, the code of Skyrim contains many enums. Some of them have already been reverse engineered and are stored in CommonLib. For example, in the file actor values, there is an enum for all actor values in the game. In your own mods, you'll use auto-numbering. It's convenient, you don't specify any values. So why are more than 100 enumerators specified explicitly here? After all, their values still go sequentially from 0. The thing is, one of the goals of CommonLib is to serve as documentation for Skyrim's code. This way, you can easily look up a number in the assembly and find the name of the enumerator being worked with. The second thing you've probably already noticed, the K prefix before all enumerators. Back in the old days, before type languages, you could accidentally use a string variable instead of a numeric one. Diagnosing that kind of error was hard. So people started adding prefixes to variable names to help identify the type. The letter C was used for char, and for constants, they used K from the German word Konstante. This approach is considered outdated. Personally, I don't like the prefixes in CommonLib, but that's how it historically came to be. Ryan used them, and others picked them up. In my own fork of CommonLib, I don't use the prefix in new enums, even though it sacrifices consistency. You can decide for yourself whether to use them or not. But for now, you know what the K is for and you won't be surprised when you see it. In this same enum, you can see a common pattern, the total enumerator. If the enumerator in your enum have sequential value starting from 0, then the value of any enumerator equals the number of enumerators before it. So, if you add one more enumerator, total, at the end of the enum, its value will automatically become the total count of the other enumerators. If you change the enum, the value of total updates. This is convenient. Total is often used as a default value or for declaring arrays. The second construct in this file shows another interesting point. Below, there is a structure actor value modifiers, which contains an unscoped enum actor value modifier, followed by a using declaration. By now, you have enough knowledge to understand what effect this has and why it was done this way. It creates a C-style enum with all its enumerators inside the scope of the structure. This way, the RE namespace don't get polluted, while still preserving the implicit conversion to uint32 for variables of type actor value modifier. An example of using this struct enum can be seen in actor.h file. In the modifiers structure, an array is created with the size actor value modifiers total. Here, two previous ideas are used: total and the enum inside a struct. The latter removes the need to write static cast. Below in the same file you can find functions that take these enums as arguments. For example, getActorValue modifier. It takes both actor value modifier and actor value. Here is how you could use it in your code. Overall, using enums in CommonLib&SKSE mods is almost no different from regular C++ code. In CommonLib code, you'll encounter both scoped and unscoped enums, as well as unscoped enum inside a struct followed by a using declaration. This preserves implicit conversions, but doesn't pollute the namespace. You'll also see the K prefix. It remains for historical reasons and is actually unnecessary. If enumerators are numbered sequentially from 0, total is often added at the end. Its value will equal the total number of enumerators. Now, regarding what concerns you as a code author. When defining an enum, it's always better to explicitly specify the underlying type. If you're writing code in CommonLib, be sure to explicitly specify both the underlying type and all enumerator values. Those are the main points of using enums in CommonLib&SKSE mods. Next, we'll be interested in the opposite task. You're not writing Skyrim, you're reverse engineering it. Skyrim's developers wrote the game in C++, and you are dealing with a compiled binary. It has no names of constants, no enums, no types, only processor instructions. Let's look at an example on Godbolt. I wrote two code snippets. One uses constants, the other uses a scoped enum. Now we'll see what they compile to. In the reading function, a 2-byte number at offset 4 bytes is read and compared to 44. In the writing function, the 2-byte number 33 is written at the same offset. The assembly came out byte for byte identical. After all, an enum is a programmer's aid. The information is erased during compilation. It's impossible to distinguish an enum from an int in assembly. The same problem as when determining a function signature. However, if you see that a variable or a field is being treated like an enum, it makes sense to work with an enum in either. There are two common patterns of working with enums: assignment or comparison with set of constants, and also switch. Your task is to figure out whether it's a known enum or whether you need to create your own, giving a name to the enum itself and to each enumerator. Now we'll open that function in ida. Instead of an enum, the arguments will be plain integers. Next, I'll tell you how to guess that you are looking at the enum in ida, how to turn constants into their names, how to create new enums, and how to change existing ones. Open the function. We'll now walk through the reverse-engineered path, figure out the enums, and replace all constants with enumerator names. As you can see, the second and third parameters are 4-byte integers. Set the correct signature by pressing Y. The function returns float. The pseudocode updates. Here is a common enum pattern, a switch on the third parameter. Depending on the value, a different pointer is written to a variable. Notice that the value hex 18 corresponds to health modifiers, hex 19 to magic modifiers, and so on. Of course, health, magicka, stamina are all actor values. Open actorvalues.h and check that hex 18 really is health. You can rename the variable to modifiers with the nk. Then set its type to a pointer by pressing Y. Make it a pointer to the type that those members have. The function is already easy to read. The switch handles initializing the pointer variable for modifiers. For health, magicka, stamina, and voice points, it uses member modifiers from the actor structure. For the rest, it uses AV storage and helper function in the default branch. Then the second argument is used as an index. Since you've already realized that the third parameter is an actor value, you can change its type. This enum exists in ida and is called actor value indices. As you can see, ida guessed and replaced the constants with names. Now the code reads even more clearly. To make the pseudocode looks perfect, all that is left is to set the correct signature for the helper function. Its return value is a pointer to modifiers, and the first argument is a pointer to this member of the actor structure. It's not yet obvious that the second parameter is also an enum. Right now, you'd want to name this variable int. Go back to the modifier structure. In ida, you can see that it accesses its only member, modifiers, which is an array of size actor value modifiers total. It's natural to assume the second argument is actor value modifiers. You probably don't have that enum yet, so let's create it. Open the local types window, press insert. Copy the enum from CommonLib. ida doesn't understand std, so remove it. Another important point. In ida, all enums are unscoped. That means all defined constants are visible globally. To avoid name conflicts, I suggest adding the enum name as a prefix. Press OK. You've created your first enum. Now change the type of the second parameter. Another interesting thing is in the first line of the pseudocode. Because the second parameter will be used as an index later, the compiler moved the value from a 32-bit register into a 64-bit one. This can happen not only with enums, but with any type smaller than 8 bytes. If you switch to assembly with tab, you'll see the move sxd instruction. As I explained in the video about function signatures, these instructions signals that edx holds an int32, a signed value. This is a reason to change the underlying type of the enum you created. To do that, use edit. Refresh the pseudocode with F5 and you'll see the cast disappear. Name the second parameter, for example, mod. Since the function returns a modifier value, it makes sense to name it getActorValueModifier. Now you can even feel good about making it green with mark as decompiled. Once you've reverse engineered a function, so you know its signature, the meaning of its parameters, and its return value, it's worth looking at the places that call this function. That will give you a better understanding of what's happening there as well. To see the list of references, press Ctrl X. Choose SetLevel. The function getActorValueModifier is called 3 times. Look, either figure out on its own and replace the constants in the first 2 arguments. All 3 calls get the damage modifier, but for 3 different actor values: health, magicka, stamina. If you need to know the numeric value of an enum constant, hover the cursor over the name. It will show it. So the damage modifier is 2 and health is hex 18. The obtained values are passed to the function restoreActorValue, whose second parameter takes the values hex 18, hex 19, and hex 1a. Have you guessed what's happening? Remember how when you gain a new level, your health, magicka, and stamina are restored? This is the very place responsible for that, and the constants hex 18, 19, and 1a are those same 3 actor values. In one of the earlier episodes, I talked about how to modify the game's assembly. If you remember, you could clear the call to the one of the 3 restoreActorValue functions, and the corresponding actor value won't be restored. So you could release a mod that makes the game harder. After a new level, you don't restore your health. To make either show an enumerator name instead of a constant, right-click on it and choose enum. A list will be open with all enums that contain an enumerator equal to this constant. The enum name is on the left, the enumerator name is on the right. If the enum you need isn't in the list, that means the enum doesn't have that value. You need to add it the way I explained earlier. When you add many enums, the lists become large and you'll need to use the search function. Find actor value indices and select it. Now the name actor value indexes health is displayed. If you need to revert to the constant, right-click again and choose decimal. Why do you think either replaced the parameters of getActorValueModifier with names, but left restoreActorValue unchanged? Indeed, the signature of getActorValueModifier says the second and third parameters are enums. In simple cases like this, IDA figures it out and shows constants as enum names. In more complex situations, you'll have to assign the names manually, just as I showed you. In this specific case, it's enough to change the signature of restoreActorValue. Make the second parameter actor value indices instead of uint32. After pressing F5, the constants turned into names. As a bonus, let's figure out the assaulter. We already discussed that this function's actions, restoring 3 actor values, happen to the player. Of course, the global variable assaulter is actually the player. Either the rename script named it incorrectly, or reader did during auto analysis. Rename the variable to player. To confirm this, find where the variable is written to. Open the xref list. On the right, you see the instructions. In almost all of them, player is the second argument, which means a read. Find the instruction where the player is the first argument. Here it is. Judging by the pseudocode, this is a destructor. The variable is zeroed out, then the player structure is deleted. Most likely we are in the shutdown function. We need to find the constructor. Good programmer is a lazy programmer, right? Here it is. The PlayerCharacter constructor is called v3 holds the pointer to the created structure. Then the pointer is written to the global variable player. Now it's clear why there are so many xref to this variable. The game code accesses the player very often. That's how working with enums in IDE looks like. Enums are created and modified in the local types window. Assembly instructions hint at the underlying type, almost always the size, sometimes the signess. IDE can guess based on type system and replace constants with enumerator names. To do it yourself, use the context menu on the constant, or hotkeys. Same way you can also revert the constant back. To see an enumerator value, hover over it. When you realize you are dealing with enums, first check CommonLib. Maybe the enum unit is already known. Recognizing an enum in IDE's pseudocode needs special attention. The general idea: if a variable or field is treated as a set of constants, not a plain number, it's most likely an enum. Clear markers are a switch or a series of comparisons against a small set of constants. Another marker is when a variable gets assigned one of several constants under different conditions. You're confident that it's an enum should grow if the constants start from 0 and go sequentially. As a conclusion, I'll show you a pattern that arises from compiler optimizations when working with enums. This happens often, and an unprepared viewer might not understand what's going on in the code. I'll demonstrate this pattern using a function from Combat AI that I've already reverse engineered. This function is complex, and reversing it goes beyond the scope of this video. I'll show my pseudocode, and we'll focus only on how enum handling looks here. You don't need to dig into the rest of the function's logic, and you certainly don't need to open it in your IDE. By the way, if you want to practice recognizing enums, there is the combat path update function, a very good candidate. It contains everything I told you and will tell you later about enums in IDE. The combat behavior advanced structure has a path field, and that path in turn has an enum field responsible for the current state. The path has several states. I haven't figured out the last two values yet, but that's fine. Here are all the places where this field is used. It's immediately clear what this path does. It checks if the state is unreachable. In this case, the combat behavior advance shuts down, an error is signaled, and then it terminates. Before that, when this condition is met, the blackboard value target unreachable distance gets updated. Look, comparing the goal found field with 2. That's probably also an enum. So, if during CommonLib advance the path becomes unreachable, the work ends with an error. Makes sense. Look at the other uses. I picked a good function. It has 3 variants of the pattern. In all 3, first a constant is subtracted from the enum, followed by either an and, a less than check, or a greater than check. And the less than check is non-strict, while the greater than is strict. The patterns share 2 things: subtracting a constant and treating the result as an unsigned number. You can confirm this by looking at the assembly. The sequence of CMP-GA instructions indicates an unsigned comparison. That's the key point of the optimization. Negative numbers have their highest bit set, which makes them large unsigned numbers. For example, -1 is hex FFFFFFF, the largest unsigned number. Therefore, if state equals 0, then state -1 becomes hex FFFFFF, and the checks fails. The values 1, 2, and 3 pass the check. 4 doesn't, because the subtraction result is 3, which is greater than 2. Do you see what this code does? Subtracting a constant from a variable, and then performing an unsigned comparison with another constant, checks whether the integer variable falls within a known range. In this case, it's the range from 1 to 3. That is, if the path state is building, moving, or waiting repath, it checks whether the actor has reached the target point. If it has, the path stops. That also sounds valid. Let's look at the second variant of the pattern. Which states qualify here? Stopped, 6, and 7, for obvious reasons. Unreachable qualifies, but it won't be processed because it was already handled above. None also qualifies, since hex FFFFFFF is greater than 2. In these cases, the CommonLib advance finishes successfully. A careful viewer will notice this is just the negation of the previous condition, but practicing with a strict greater than comparison wasn't useless. Finally, the last pattern, end. Hex FFFFFFD is all ones except for bit number 1. An end with this number clears bit number 1. If after clearing there is still a non-zero result, it means the number had other set bits. So the condition excludes all states where subtracting 1 gives either 0 or 2. That means it excludes only building and waiting repath. Generally, if you don't want to think, you can check such expressions on Godbolt. You simply write the expression inside a function, and then add static asserts. For the asserts to work, the function needs to be constexpr, and you need to set a recent standard flag, like C++ latest. So if the path was previously being built, and now it's neither being built nor waiting repath, then an attempt is made to update combat target location. Some checks, like variable equals one of these constants, are optimized very well by the compiler. If you manage to decipher such magic and understand that it's really checking equality with constants, then you are looking at an enum. IDA often manages to show this in readable pseudocode, but not always. The compiler doesn't aim to confuse you, it just generates optimal code. IDA's goal is even less to confuse you, it aims to show you the clearest possible pseudocode that matches the assembly. Trust me, it already does a good job. Try finding a switch in pseudocode and see how complicated it looks in assembly. But sometimes you have to think to understand what pseudocode actually means. A common compiler optimization related to enums is checking whether a variable value falls within a range using subtraction and unsigned comparison. In this function, this optimization appeared twice, and we were also lucky to stumble upon an optimization with AND. Often IDA displays readable pseudocode, but it didn't decipher this particular optimization. Things are much harder with bit flags and combinations of bit fields and enums. IDA can't display work with this construct nicely, so you have to think while reading the pseudocode. The next two videos will be dedicated to that. Originally, I wanted to make one video and cover all three constructs at once. I had already gathered the material, including examples in IDA. I even wrote half of the script for the video. But it turned out to be so much that I got tired and took a break. That's exactly why I decided to split the video into three and make this video a preparation for the next two. The next two videos will be structured similarly. First, I'll explain the motivation for using the construct, then its C++ side, then point out details regarding CommonLib, and finally, we'll practice in IDA, recognizing work with these constructs and improving the pseudocode where possible. As you may have noticed, not all my predictions about the topic of the next video come true. But since I've already gathered the material, it's be harder for me to change my mind and pick a different topic. And that's all for today. Now you know everything necessary about enums for SKSE modding. Have a nice day. Enumerate your thesis, load C++ knowledge. See you in the next videos.